Good morning, students. Today we will see Introduction to Manipulator Kinematics. So it's coming under your second module. Already I have explained you the basic of kinematics. I will touch that further. I will go through the forward kinematics, inverse kinematics, and the kinematics if the gravity loads are playing a vital role. All these things we will see in this class. So as like we have seen in the class, the body, arm and wrist assembly, sometimes called as manipulator. The manipulator consists of joints and links. So joints provide the relative motion. Links are rigid members between joints. Various joint types, that is linear and rotary, we have seen, and each joint provides a degree of freedom. So as I told in the class, degree of freedom means number of independent motions. So in this manipulator you can see you are having a base, you are having a link 0, joint 1, joint 2, link 1, link 2, and joint 3 and link 3 and end of arm. So coming to manipulator kinematics. In order to develop a scheme of controlling the motion of a manipulator, it is necessary to develop techniques of representing the position of the arm at points in time. So the robot manipulator can be defined by two basic elements. One is joints, another one is links. Links are assumed to be rigid structures that connect the joints. So how to position the robots we have discussed in the class. Further I want to give you in detail. So consider a two-dimensional 2D area of freedom manipulator type RR, that is Revolute and Revolute manipulator. You can see the schematic diagram. The link 1 is having a length of L1 and the link 2 having a length of L2. And the link 1, which is having an angle with respect to x-axis, is θ1. Similarly, the link 2, which is having an inclination of θ2 with respect to link 1 axis. The final or end effector point is, or the end of the two links position is PW x comma y. So it's a planar mechanism. So we are having x and y. So figure 1 illustrates the geometric form of the RR manipulator. As I told you, RR means revolute and revolute. The position of the end of the arm may be represented in a number of ways. So I have already told you, based on joint, otherwise in terms of world space. One way is to utilize the two joint angles, that is θ1 and θ2. This is known as the representation in joint space, and we may define it as, that is P, the point Pi from θ1 comma θ2. The another way to define the arm position is in world space. This involves Cartesian coordinate system. This is external to robot. So the Cartesian axis system is often located in the robot space. The end of the arm position would be defined in world space as PW x comma y. So it's related to the Cartesian. Pi is related to θ1 comma θ2. So these are the two ways we are representing the position of the end of the robot arm. So further we will see in detail. So how to represent an arm's position. So going from joint space to world space is called forward transformation, otherwise direct transformation, otherwise direct kinematics. So going from world space to joint space is called the reverse transformation, otherwise reverse kinematics, otherwise indirect kinematics. So forward transformation of a 2D is of freedom arm. So we are going to see how to calculate it for the Revolute and Revolute manipulator. So consider the figure, two-dimensional, a 2 degree of freedom manipulator R type. Already I have explained you L1, L2, theta 1 and theta 2. So the position of the end of the arm in world space can be determined by defining a vector for link 1 and another link 2. So you know that I am taking here as an R1. R1 is the end of the link 1. So which is having an angle of theta 1 with respect to x-axis. So it is giving the x comma y coordinates as L1 cos theta 1 and L1 sin theta 1. Similarly, if I am taking R2, that is at the end of the link 2 from the origin, it will be L2 cos theta 1 plus theta 2 and L2 sin theta 1 plus theta 2. I am saying the value of x comma y. So vector addition of above equations yields the coordinates of x and y of the end of the arm in world space. So x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Similarly, y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So coming to the reverse transformation. So now we are going to calculate theta 1 and theta 2 in terms of L1, L2 and x comma y. So in many cases, it is important to be able to derive the joint angles given at the end of arm position in world space. So example, the robot controller must be compute joint angles required to move its end of arm to a point in space defined by the point's coordinates. So consider the same figure. So to calculate the reverse transformation, there is a possibility of only two ways. So you can see that the two possible configurations for reaching point x comma y. So one is above, another one is below. So the arm at point P x comma y indicating two possible configurations to achieve the position. So these two determines whether the element is to make an angle theta 2 is greater than or less than 0. So in this case, let us assume that theta 2 is positive. So I am taking the below one consideration. I am not taking the above configuration. I am taking the below configuration. So using the trigonometric identity, so we know that cos A plus B is equal to cos A cos B minus sin A sin B. Similarly, sin A plus B is equal to sin A cos B plus sin B cos A. So take the schematic representation. So based on that, we can write the equation 3 and 4. So 3 and 4 is this one, x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So these two equations, so I am writing with respect to the above trigonometric relations. So you can see x is equal to L1 cos theta 1 plus L2 cos theta 1 cos theta 2 minus L2 sin theta 1 sin theta 2. Similarly, y is equal to L1 sin theta 1 plus L2 sin theta 1 cos theta 2 plus L2 cos theta 1 sin theta 2. So squaring on both sides and adding the two equations, it will give you the parameter of cos theta 2. So theta 2 is nothing but the joint angle with respect to the link 1 of the second link. So the answer you will get x square plus y square minus L1 square minus L2 square divided by 2 L1 L2. After you are solving that sin square theta plus cos square theta is equal to 1 and neglecting all other terms, you will get the final equation as that cos theta 2. So based on this equation number 7, you can calculate the joint angle of theta 2. So to calculate theta 3, so draw the schematic diagram with respect to alpha and beta. Same diagram, just a schematic diagram, you can modify it. So the alpha is nothing but the angle, the trigonometric angle which you are making with respect to the horizontal of the link 1 and link 2. The diagonal is known as alpha, and the beta is the another one which is making an angle of the entire angle of the diagonal to the x-axis, and theta 2 and theta 1 are same. So again I am explaining you, alpha is nothing but the link 1 with the diagonal line of the triangle alpha, and beta is the entire angle with respect to the x-axis, and theta 1 and theta 2 are link with respect to link 1 and with respect to link 2, the angles. Link 1 is with respect to the horizontal axis x, and link 2, the theta 2 is with respect to the link 1, the link 2 angle. So all these things we are making to solve what is theta 3. It's simply a geometrical representation. So if you are going through some other ways also, it's okay. It's not a problem. Whatever possible way, we have to find out the solution for theta 1. So if you are taking this trigonometric relations, the tan alpha will give you L2 sin theta 2 divided by L2 cos theta 2 plus L1. Just you can make the relations, you will get it easily. So alpha, you know that, as I told you, it's an inclined angle of a diagonal line which is drawn in the figure 3 with the link 1 diagonal is alpha, diagonal line, and the link 1 up to that is alpha. And the beta, you know that the entire angle which is made by, it is nothing but opposite by adjacent, so y by x. The entire length along y axis is y, and the entire length along the x axis is x. So tan beta is the entire. So based on 8 and 9, using the trigonometric identity, so you know that tan a minus b is equal to tan a minus tan b by 1 plus tan a. So we get finally, if we are substituting that, so theta 1 is nothing but, you know, that beta minus alpha is on the figure 3. So theta 1 is nothing but beta minus alpha. If you are substituting that, you will get the equation number 10. It's very simple, just work it out. So tan theta 1 is equal to y multiplied with L1 plus L2 cos theta 2 minus x L2 sin theta 2 divided by x whole bracket L1 plus L2 cos theta 2 plus y L2 sin theta 2. So in this way you can calculate theta 2, that is joint angle with respect to the link 1 and the link 2. Link 2 angle with respect to the link 1. Similarly, you can calculate theta 1, which is made by which is the angle made by the link 1 with respect to the horizontal axis x. So knowing the link lengths of L1 and L2, So we are now able to calculate the required joint angles to place the arm at a position x comma y in one space. So this is the simple planar mechanisms to calculate the forward and reverse transformation. So just draw the figure 3 clearly, and then you can work it out. It's very simple. So try to understand alpha, theta, beta and theta 2. Just to close the line from x comma y, draw a vertical line which is parallel to y, and extend the horizontal axis x line. You will get a triangle. Based on that, you can solve this problem very easily. So general things. Accurate control of the manipulator requires precise control of each joint. The control of the joint depends on knowledge of the forces that will be acting on the joint and the inertia reflected on the joint. These are the very important parameters. So I want to give it as a general note. So while these forces and masses are relatively easy to determine for a single joint, it becomes more difficult to determine them as the complexity of the manipulator increases. Hope you understand the 2 degrees of freedom is very simple compared to the multiple degrees of freedom. So next very important thing is coming to the static analysis of the manipulator. So consider the same RR manipulator. I am taking the 2 link arm forces and the torques diagram. How to draw this? So F1, F2, and I am taking as a static condition. So sum of the forces acting on the system is equal to 0. So based on that, I am drawing this diagram, 2 link arm forces and torques. So if I am saying F1 and F2, which is F1 is acting on the link 1 on the origin, and F2 is acting on the link 2 of the origin, and the final value is F. So if I am nullifying the values, then only it is called as static analysis. So consider the 2 link arm forces and torque system. So you know torque is used to rotate the, it's a rotating, actually it's a moment due to the force. So you know L1, L2, and you know R1 and R2. Already I explained what is R1 and R2 and L1 and L2. So consider the free body diagram. You know T1, T2 is acting and is clockwise and another one is counterclockwise. And you know F, F1, F2 and F. So F1 is force acting at the joint 1, F2 is force acting at the joint 2, F is acting at the end of the arm. So by considering the torques required by the joints to produce force F at the tip of the robot arm, as shown in figure 4, by balancing the force on each link, because it's a static analysis, you have to balance it. So F1 minus F2 is equal to 0, obviously, and F2 minus F should be equal to 0. So this is nothing but the balancing the force on each link. It's very important to calculate the static analysis. So F1 minus F2 is equal to 0, F2 minus F is equal to 0. So obviously F1 is equal to F2, that is equal to F. So this is the way only we have to calculate the static analysis of the 2 link arm force. So consider again this one. Further I want to explain this. The torques or the vector cross products of the forces on the link vectors are. So now you have to know that it's a cross product, try to understand that. It's not a dot. So T1 is equal to, so if you are taking the T1, the torque to T2 plus R1 into F. So I'm taking with respect to the origin. T1 is equal to T2 plus R1 into F. So if I'm taking T2, R2 into F. So when I am considering the lower link, I have to calculate the torque of the upper link also. If I am considering only the upper link, I have to consider only about its forces and its radial distance. It's a simple mathematical relation. Try to recollect your engineering mechanics, then it will be very easy. So therefore, if I am taking T1, so based on the equation 14, so R1 plus R20F, obviously. If you are taking F is equal to Fx comma Fy, try to understand the condition. If it is F is equal to Fx comma Fy, then you will get this equation. T1 is equal to the entire equation. So you know about X, how to calculate, Y, how to calculate, based on the previous forward transformation. L1 cos theta 1 plus L2 cos theta 1 plus theta 2, comma L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So the first one is along x-axis, another one is along y-axis. So you know how to multiply the term. So this 17 equation is the. So again I want to recollect it. It's actually cross product. Since the vector product is A cross B cross C cross D is AD minus BC. Try to understand this. So if you are multiplying this, we will get T1 is the equation of L1 cos theta 1 plus L2 cos theta 1 plus theta 2 multiplied with the Fx, the force acting on the X, minus L1 sin theta 1 plus L2 sin theta 1 plus theta 2 multiplied into Fy. So 18th equation is very important to calculate the torque acting on the link. And T2 similarly, L2 cos theta 1 plus theta 2 into Fx minus L2 sin theta 1 plus theta 2 into Fy. So the 18 and 19 equations are given the torque equations with this system. So therefore, given force vector F is equal to Fx comma Fy, the torques required by each joint to generate that force at the tip can be compared using preceding process. So why I am explaining all these things is it will look like you are coming across all the basics of engineering mechanics. Same thing, if you want to design any manipulator arm which is in serial manipulator or parallel manipulator, you have to consider this as a link and joint, links and joints. Then the analysis will be very easy. So in order to calculate the force generated by the end of the arm, given the joint torques, we must solve the equations for Fx and Fy. The solution is obtained by subtracting equation 19 from 18. Then substitute for Fy using the value in equation 19. As slowly you do, you will get the answer. So this results in an expression for Fx, T1, T2, Theta 1 and Theta 2. So all these things you will get it. After simplification using trigonometric identities as obtained earlier, we get T2, L2 cos theta 1 plus theta 2, Fx minus L2 sin theta 1 plus theta 2 into Fy. Similarly, you will get Fx. So all these things relations you have to put it and then you have to solve it. The objective is based on the torques you are calculating the force. Similarly, Fy. So Fx and Fy you will get based on the. So the entire process is, because it's a planar mechanism, it is acting along X and Y. So we are using a trigonometric identities to solve this. So slowly go through and calculate the Fx and Fy. So the ability to determine the joint torques on the components of forces applied at the wrist or tool are useful for controlling the arm when it must contact the environment. It's very, very important. So any robotic designs, you have to know that what are the forces and the torques are acting on the system. Then only you can control the arm effectively. It's very important in terms of design. And simple question I want to ask you. To measure the forces and torques in robotic applications, we use, so most of them will think something else because Sir is teaching you kinematics, but it's very simple. Somebody would have been come across, somebody would have said what is the answer. So now the answer is simple, sensors. So hope you will understand what I am explaining. It's very basic compared to your 6 degrees of freedom. This is very fundamental. Just sit with your friends and calculate the forces and torques of the RR manipulator. So once you are solving this, the same thing you can use for all the rotational manipulators, which is in CV. So next very important thing is the previous analysis we did not consider the gravity. So now we are going to consider the gravity and then we are going to solve the equations. So gravity was included in the previous analysis. It can be included by adding the forces exerted by gravity on each link to the force balance equation in the previous section. So see here now, so the effect of the gravity, you know that the gravity will act at exactly center of the link. So gravity forces and torques. So both the forces acting at the center of the each link, which link have masses m1 and m2. So balancing the forces due to gravity only we get, very important, F2 is equal to G, F1 is equal to F2 plus M1G. See this one you know that. So link 1 should be bulky, I used to say always when I am explaining about serial manipulator. So this is the reason behind that. Because the link 1 should carry or able to carry the load of the link 2. So the cross products of the link vectors R and the forces gives us the torque due to gravity on each joint, as like previous. So Tg2 is equal to minus M2 R2 and G by 2. So you have to know that why it is minus. I'll go through the free body diagram. You will understand why it is minus. So that is equal to G M2 L2 cos theta 1 plus theta 2 divided by 2. This is the equation of Tg2. So similarly Tg1. So you know why I am considering half of the mass for M1 and why I am considering the full mass of the M2. Because in mass, when I am considering the torque at 2, I am considering half of the mass of the link 2. When I am considering torque 1 with respect to the link 1, I have to consider the entire mass of the link 2. So only it is M2. So M1 by 2 plus M2 L1 cos theta 1 plus M2 L2 cos theta 1 plus theta 2 by 2. So I have to consider both things, both the links when I am considering torque 1. So if the manipulator is acting under gravity loads, then these torques must be added to the joint torques to provide a desired output force. Again I am saying that if the manipulator is acting under gravity loads, then these torques must be added to the joint torques to provide a desired output force. So all the manipulators which are functioning in industry should add the gravity loads. So another footnote, the arm can be constructed with as low mass as possible. More of the motor torque will be used to provide forces at the end of the arm for doing useful work rather than just supporting the mass of the link. And I repeat, the arm can be constructed with as low mass as possible. More of the motor torque will be used to provide forces at the end of the arm for doing useful work rather than just supporting the mass of the link. Gender, so arm image, yeah. So when the arms are very close, the minimum inertia about J1 is secure. So the maximum inertia is when the robot arms are in fully extended conditions. So when it is minimum inertia, so when the arms are very close to the close to each other. Okay, when it is maximum inertia, when the arms are fully extended. So this is simply a dynamic forces and torques of a TRR robot. You know the T means twisting, R means revolute, and R means revolute. So you can see a schematic diagram of the TRR robot, how it will work. So you can see T1, T2, T3, T1, 2, 3, T3, 2, T1, 3, 2, 2, 3, T2, 3. So you know J1, J2, J3 all are nothing but the inertia forces. T1, T2, T3 are nothing but the torques, joint torques. So it's a simple schematic representation of the dynamic forces and torques for a TRR, twisting, revolute robot. So the torques required to derive the robot arm are not only determined by the static and dynamic forces described above. Each joint must also react to the torques and other joints in the manipulator, and the effects of these reactions must be included in the analysis. So if you are designing any kind of a robot, so you have to come across static and dynamic forces. Apart from these torques, you have to know that each joint must also react to the torques and other joints in the manipulator, and the effects of these reactions, that is very important, must be included in the analysis. So design engineers, mechatronics design engineers, you can concentrate more on these kind of aspects also, instead of playing only with microcontroller and some sensors. Calculate and then work it out, and then you execute it. So if the arm moves relatively high speed, the centrifugal effects may be significant enough to consider. The arms relatively high speed. So configuration of robot controllers, general already I discussed in the class, but again I want to put it. So this is the way the robot controller will be there. There will be an input and output device. Program memory will be there. Executive processor will be there. Mathematical processor will be there. It's a general one, a general robot controller. But nowadays it's a advanced controller scheme. But this schematic representation will be there. So J1 means servo controller, J2 means another servo controller, J3 means another servo controller. It's nothing but the servo controllers are nothing but the joints. Each joint it will have a servo controller, and it will have a power amplifier, and it will have a joint actuators. All this. So this is the step by step. Otherwise, the flow of the robot controller elements, how from the higher to the lower. So first one, you can say the motion commands are executed by the controller from two possible sources. One is operator input, second one is from program memory. And commands are downloaded from program memory under control of executive processor. And for each command, the executive processor informs the mathematical processor of the coordinate transformation calculation that must be made. When the transformation computations are completed, the executive processor downloads the results to the joint controllers. Position commands. So you have to know the order how it is working. So when the transformation computations are completed, the executive processor downloads the results of the joint controller's position commands. Each joint controller then derives its corresponding joint actuator by means of a power amplifier. So any questions you can mail me or you can meet me on Friday. Thank you, students. See you on Friday. Thank you.